Okay, so I'd like to do a similar problem, but this time I'm going to change the number of known and unknown. Let me switch board. I'm going to pick a vector A going like this. Let's imagine I know the direction of A, 30 degrees. Let's imagine I know vector C. I know its direction, obviously. Let's imagine I know its magnitude, 3. And then I'm going to pick another vector B defined as 60 degrees, and I have no idea what the magnitude is. So this time, instead of knowing entirely 2 vectors and trying to looking for the third one in both direction and magnitude, I will know a portion of them. So C I know entirely, A I only know its direction, B I only know its direction. And again, at this stage of chapter 1, you can practice as much as you want. So keep practicing by making up those problems. Pick, you 2 magnitude as unknown, and then do the same problem by picking 2 direction as unknown. And then you can try not knowing the magnitude of A and not knowing the direction of B. So keep practicing all possibilities. And since you have done the problem with, let's say, all the known, then you can always check your answers. So keep practicing, get fast at it. I'm choosing this case because this, if I'm going to do it correctly, I hope, will force us to use system of equations. So let's express A in terms of component notation. A will be 30 is defined from the positive x going counterclockwise. So could you give me the functional form of A in component notation? In this case, of course, we do not know the magnitude of A, so we're going to call it A. Similarly, since we don't know the magnitude of B, we're just going to leave it as the variable B. So could anybody give me the functional form of the representation of vector A in component notation? Oh no, okay. A cosine 30, yep, excellent. A cosine 30 plus A sine 30. Okay, no problem there. 30 was defined from the positive x going counterclockwise, the x is cosine, the y is sine. Let's do the same thing with B. Which triangle are we going to use? The angle is defined between this line and this line. So definitely we want to pick this right angle triangle. So what will be the decomposition of vector B? And watch out for the sign. Yeah, excellent. Minus, because bx is going left, b cosine 60. Oh, I'm sorry. Cosine, okay. Cosine 60. And then plus b, because it's going up, sine 60. Cool? Everybody agrees? Cosine adjacent, okay, that's good. C, well, C is easy. Okay, cool. C, there is no I, and the J is negative. Okay, that's what we have. And now we know that, oh, I'm sorry, I forgot to tell you. Sorry. A, B, and C are 3 vectors in such a situation that the system is at equilibrium. So that we know that the sum is equal to 0. As we were trying to find the magnitude of A and B. So as we apply this condition, we know that if we add all those vectors, we better end up with the 0 vector. So it means that A cosine 30 square root of 3 over 2 plus the x component of b, which is minus b cosine 60i plus the 0i of c. If we add all those guys, we know we have the 0 vector. And again, I'm stressing that vector because if a, b, and c are vectors, 0 going to be a vector. And this is the same as 0 times I plus 0 times j. Right? So now if I add this plus this, then I end up with 0. And similarly, if I add the I, the j's, this plus this must give me 0i. So now I have my second equation. A sine 30 is 1/2. Sine 60. Oh, I forgot to evaluate cosine 60. Sorry. Cosine 60 is 1/2. Sine 60 is square root of 3 over 2. Plus, whoops, minus 3. And that is 0j. Okay? I'm being ultra anal here. Because, as you guess, what I'm going to do now is I add up all the i's together, all the j's together, set them up equal to 0. What I can do is nuke all the i's. That was supposed to be a j, sorry. And then nuke all the j's. So really now I have two scalar equations, which is nothing else but a system of two equations and two unknown. So you've done that in basic algebra where a might have been x and b might have been the y. So I can rewrite this as square root of 3 over 2a minus 1/2 b is equal to 0, and then 1/2 a plus square root of 3 over 2b. And I'm going to move the constant time on the other side, the constant term on the other side, so 3. Now we're back to basic algebra. Here we have two options. Actually, you have three options. You can either use the substitution method, which involves solving for either a or b, you decide, say from the first equation, again you decide, and then replacing that value of a in the second equation, which then depends only on the variable b, so that you can solve for it, and then you can replace it back in any of the two equations to get the a. Okay, so you've done that in high school, you know how to do this. Second method is to use the addition method, which is that you want to pick any of those two equations, multiply it by a clever chosen factor, such that as you add those two equations together, one of the two terms, either a or b, disappears. Yes, exactly. So Anthony suggests that if you want to use the addition method, you can multiply the first equation by square root of 3, which will allow you to get rid of the b as you then add up the two equations together. Okay, remember that you can multiply an equation by any number, divide it by any number, or in general, apply any mathematical transformation to an equation if you apply that transformation to every term. So if you multiply every term by square root of 3, you don't change the equation, so it's the same equation, and you take that same equation, add it up to the second one, and in this case, after choosing square root of 3, the term b will disappear, and you will only be left with the term a and a constant term. Then you can solve for a. Once you get a, you can go back to either of those two equations, plug in it, and then solve for b. That was the addition method. The other method is the matrix method, which, if you have taken Math 103 in the UH system, you've seen that method. It's called, oh yeah, I forgot what it's called. Cramer? Yeah, maybe Cramer. It's based on the concept of determinants. I would like to show you that method tonight, because even though it is most likely not the method that you're going to be using until chapter 12, I believe, until we reach momentum. And even then, you might choose to use a calculator or any other method, because we're only going to be dealing with a 2x2 system, two equations to unknown. I'm sorry, John 03 can solve the A. I believe, okay, you got it. I believe Anthony was talking about this equation that he wanted to multiply by square root of 3. And if he does this, it's going to be, yeah, canceling the b. Are you clear, John? Okay, cool. Yeah, I'm sorry, I forgot what I was saying. Oh, yeah, Cramer, matrix. I still want to introduce it today. So at least you see it once. And again, you may not end up using it this semester, unless you want to. But the reason why I want to introduce it this semester is that you will definitely need it next semester if you take C270. Because in most problems in 270, it will be in 3D. So solving a system of 3 equations, 2 unknown, using the addition and or the substitution method takes a little while. But, okay, so let's do it together. If we multiply the first equation here by square root of 3, the first equation becomes 3/2 times a minus square root of 3 over 2b is equal to square root of 3 times 0, which is still 0. Then the second equation, I ain't going to touch it, but I'm going to write it right below it. So this allows me to see that if I add equation 1 with equation 2, this will become 2a, and those two, as I add them up together, will give me 0. And 0 plus 2 is 3. So a is 3/2. And then you can solve for b by plugging it in. Okay, good. So again, I forgot what I was saying. Oh yeah, sorry. I want to go through that method anyway, because in C270, most of your problems in 3D, and this method will end up being much faster than the substitution and the addition, which is longer, and it's easy to make mistake. Worse, when I used to teach C271, some of the problems at the later part of the semester will require you to set up a system of 7 equations, 7 unknown, all the way up to 11 equation, 11 unknown. Now try to solve such a system using addition method or substitution, and I'll see you tomorrow. It's going to take you 4 hours. So the only way to survive such a system is to use a determinant and the Cramer's method, or use your calculator. If your instructor allows it, go for it. But make sure you bust up the manual and you read it. But if you know the calculator farts or whatever, you can always go back to a solid fast method, which again might look overkill for 2x2. As you increase the number of dimensions to your system of linear equation, it gets way more and way more efficient. So let's use another screen. Hang on, I need to memorize this one. Okay. Let me show you this method. So we had square root of 3 over 2a minus 1/2 b is equal to 0. I'm going to write the other equation right under it, as I did earlier. 1/2 plus square root of 3 over 2b. And the trick here is to align all the terms together. So all the a's are right here, one above the other. All the b's, same thing. And on the second equation, I had a stupid constant. So I'm going to kick it out on the other side of the equation. So everything on the right-hand side are just a bunch of constants. Okay, so that's my system of equations. I'm going to rewrite it and transform it so it looks like a matrix manipulation, but it will have the exact same information as this system. I'm just going to write it down and I'm going to explain what it means. Hopefully you've seen matrices, so it will be nice and simple. If you haven't, just bust up any basic algebra book and in 5 minutes you can catch it. I'm going to put my A, B, 0, 3. So we need to refresh ourselves. concerning the multiplication of matrices. If you have a 2 by 2, which is the first matrix, you multiply it by 1 by 2, which is the AB matrix, you end up with a 1 by 2, which is a 0, 3. And the way that matrices multiply each other is you're going to take the first term, square root of 3 divided by 2. You're going to multiply it by the first term on the adjacent matrix, which is A. Then you're going to look at the second term of the first row, which is minus 1/2, and multiply it by the second term of the second row of the second matrix, which is B. So pretty much what we end up doing is this guy times this guy plus this guy times this guy. This should give you this guy. Then we're going to take the other row. This first term times the first term plus the second term times the second term must give you this one. It's that easy. That's how matrices multiply each other. So as you can see, if you reproduce those steps, you realize that it's nothing else but our systematic equation. Square root of 3 divided by 2 times A, first term, plus minus 1/2 times B is equal to 0. Bang. Second equation is embedded on the second row. 1/2 times A, this one, plus square root of 3 over 2 times B, this one, is equal to 3. Okay, so all we've done is reformat our systematic equation into matrices. Now the rest is simple. We're going to calculate what is known as the determinant. So I'm going to call this matrix matrix I. And I'm going to calculate the determinant of the matrix I. For a 2 by 2, it's easy. You use what we call the fish method. Fish method is this times this minus this times this. So that's why I call it fish, just like this. So square root of 3 divided by 2 times square root of 3 divided by 2 minus the product of the two others, which is minus 1/2 times 1/2. That's the determinant of a 2 by 2 matrix. So in this case, we have 9 divided by 4 minus 1/4. That's 8/4. Oh, that's 2. Oh, nice. Okay. And then the recipe is to calculate A, and the A will be the determinant of a new matrix, which I will explain, divided by the determinant of the original matrix. For B, same thing. Determinant of a new... Oh, I'm sorry, it was 3? Oh, yeah. Thank you, plus. So that's 10, whoa, so that's 10/4. Oh, 3/4. Whoops. Okay, I'm sorry. Oh yeah. Thank you. 3/4, 1/4, 1. Is that correct? Is it better now? Okay. Thank you. Sorry about that. So for B, it's going to be the same thing, divided by the original determinant of the original matrix. Right? So that new matrix for A is very, very simple. It's the same as the original matrix, except I am going to substitute the first column. Remember, the first column are all the terms that multiply the term A, and the second column are all the terms that multiply B in order for us to get this system. So I'm going to take this matrix, but I'm going to replace the first column, because I'm dealing with A, with the constant term column. That is, I'm going to put 0 and 3 and keep the rest as the same. And for B, I'm going to do the opposite. Since for B, all the terms that multiply B is the second column, I'm going to replace this second column by my constant term column. So the first one is the same, 1/2, but the second column is going to be 0, 3. Yeah, and then I calculate the determinant, which is the same thing. I use the fish. So 0 times square root of 3 over 2 is 0, minus 1/2 times 3. Whoops. Divided by the one we had. And similarly, square root of 3 over 2 times 3. So that's 3 square root of 3 divided by 2. Minus 0 times 1/2, which is minus, divided by 1 again. So in this case, A will be, I guess, 3. That's nice. And this one is 3 squared over 2. Okay? Now again, it seems like it's an overkill method for 2 by 2. You would have been much faster by using the addition and the substitution method. But as your system of equations dimension increases, 3 by 3, or especially 4 by 4 or 5 by 5, this is a much faster method. It's even faster due to the fact that most of you folks have fancy calculator. Ah, I goofed again. 3/2. Yeah, I forgot that half. Thank you, Williams. Thanks. Yeah, another reason why this method is nice is because your calculator are so performant that they all can do a determinant calculation. All those TI something, 80, blah blah, 90, all those guys have the function of the determinant. So you can just enter those 4 factors or 9 factors or 16 factors, press the button, bang, you got a determinant done. Yeah, excellent. Yep. So it's nice. So you can use the calculator to help you out and go faster using this method. And again, in C270 and C271, if you're taking at KCC, guarantee you're going to have to use matrices. Guarantee you're going to have to use this method. There's no way around it. Especially in 271 when the dimension of your system is going to be so high. If you try to solve it by hand using the addition or substitution, it's game over. You're never going to finish the test. So you have 2 options. Either you use the calculator and learn to use it very efficiently, and or at least learn this method so that if you find yourself in a deserted island, you have no calculator, then you still can do this problem. Well, if you're bored, something. Okay? In general, you always want to find ways, backup methods, so that if something goes wrong, you have a calculator or whatever, you have it in your head. Okay? You're totally independent of technology. I'm not dismissing technology, but I'm saying if you know how to do it yourself, it's always better. You never know what can happen. Okay? Questions on this? So I believe there is a link on the website that says mathematical method, and if I recall, I put some information about this on that website. So if you'd like to practice a little bit more or read about it more, check it out. Otherwise, you can Google determinant and Cramer's method through Google. Yeah, that's the one. Cramer's rule. Thank you. Cramer. Yeah, another Cramer, not that Cramer. Sorry, I'm thinking Seinfeld. Okay, questions on this?